Today we are going to focus on the next interpretation of derivative, and that is rate of change. So let's start by bringing back the mathematical definition of derivative right here in this box, f prime of x. F prime of x is the derivative of f with respect to x. And by now we know that this corresponds to the slope of the hypotenuse of the smallest right triangle. Well, a lot of things are going on here, right? So let's go over this one by one. So f prime of x is equal to, first, the slope of the hypotenuse of the right triangle. So that's definitely delta y divided by delta x, or in other words, the height of the triangle divided by the base. So for delta y, we have these two terms, f of x plus h minus f of x. These two are for delta y. It's small step, small distance in y direction. And now we divide these two terms with delta x divided by delta x. Delta x is a small step, small distance in x direction. So we are talking about the base of the right triangle here. And we also know that the length of the base of this triangle is h. So let's put h down here. H, the length of the base of the right triangle, which is delta x. If you happen to forget about all these terms, all these variables, that is okay. We talked about this before, so you can always look up the old lectures. So now what we have here is the slope of the hypotenuse of the right triangle. But we have a little bit of a problem here. The triangle that we have at this moment is large, and that is not good. We want it to be as small as possible. We want it to be smallest. And we can make that happen by putting a limit in front of these terms. So let's do that. Let's have a limit right here. And now we want the base of this right triangle to be as small as possible, which means that the length of the base, which is h, has to approach 0, go to 0. And there you go, we have the definition of derivative of f with respect to x. So let's make a note at the top here. This is the definition. The only definition we need of derivative of any function out there, but it has to be called f of x. Of f of x. Now, this is the only definition that we need. And once again, it comes down to this simple concept. It's the slope of the hypotenuse of the smallest right triangle. Now that we have the definition, let's talk about the interpretations of f prime of x. And let's do that on the right-hand side. So let's have interpretations right here. So it's going to be about meanings, concepts, ideas, and how we perceive derivative. Okay, interpretations of f prime of x. What about we assign a point to this f prime? Let's say that at x equal to a, at a particular point. So interpretations, meanings, concept. What is derivative to you when you hear this word? What is the first idea that comes into mind? Derivative. We actually talked about this before, so let's bring that back here. The first idea that we had is this. When you heard derivative, you think of slope. So first one, slope. Slope of what? Slope of the function fx itself. So slope of the graph of fx. Now, let's take a look at this interpretation. We have a problem here too. Slope of the graph of fx. Usually the graph of fx that we have is not straight. Usually it's curvy. So how are we supposed to find the slope of a curvy line? So that is not clear, right? And that's why we realize that this interpretation that we have right here is not strong enough. And that's why we move to the stronger one, number 2. Stronger interpretation than the number 1. So the idea is still here, the slope of something. But here we have the slope of the tangent. Slope of tangent instead. So now we have a straight line to work on. So tangent right here, straight line. With a straight line, of course we can find the slope of that, no problem. So this is a better interpretation of f prime of x. So tangent has to be 2f of x. And of course has to be at x equal to a. So with this linear line, no problem with finding the slope value. Now these two are the interpretations we worked on, and today we are going to move to the next one, and that is the third one right here. Number 3. We are going to look at a derivative as a rate of change. So today it's going to be about rate of change. Now let's take a look at the main difference between all these three. Number 1 and number 2. The main idea is the slope. Right? We have the slope here, and here is also slope. But for number 3, the main idea is the rate. So it's quite different from number 1 and number 2. But they are all related. They are the same f prime of x. So how are they related? Let's take a look here at the left hand side. So here we have dy divided by dx. And by now we know that this is the derivative of y with respect to x. And we can use this notation, y prime. First derivative of y with respect to x. Now let's take a look at a few things here. So we have these two d's. D at the front of y and d at the front of x. What are they? They actually have some meanings. So let's take a look here. These two d's. D stands for differential. What is that? Differential. It means a very small change. Really, really small change. Smallest change. In other words, smallest delta. So in terms of meaning, this is about the change of y and change of x, except that it's really, really small. So it's going to be similar to this, delta y divided by delta x. Change in y divided by change in x. Same thing, except that here is just so small. Make it small, and you get the differential d. Now we are going to put everything here together and translate these into words. So what does it mean here? Alright, change of y divided by the change of x. So let's write that down. Change of the variable y. So the main thing is right here. We want to observe y with respect to or divided by. With respect to, compared to. Okay, here is with respect to. Or you can say that it's compared to. Compared to what? The change in x. So we have the change in x down here. Change of x. So we want to know how y changes when x changes. Alright, so that is sort of like observation here. Now, I'm going to modify this dy by dx a little bit to change it to something a little bit different. So let's take a look at this one on the right hand side. So I keep the numerator dy the same, differential y. Small change in y, just the same. But now I'm going to do something with the denominator. Instead of having dx, I'm going to put dt instead. So here, really small change in t. And t right here stands for time. So t right here is time. Now we are going to translate this into words again. The same way. Once again, this is about the change of y variable. Change of y variable with respect to or compared to change in time. Now we have the change of time. And the key word is right here, time. So we have this time. We want to observe how y changes when time passes. So I translate this to rate of change of y. It comes from the observation of something over time. So this becomes rate of change, rate. When you see this word, it's usually related to time, right here. Rate of change of y variable. Once again. And of course we have this hidden with respect to time. Same meaning. Change of y with respect to the change of time or the rate of change of y alone. Now the key word is right here, rate of change. And it's going to correspond to derivative f prime of x. Now let's take a look at some rates of change that we have seen before, and most of them are in high school physics. So let's take a look at some of them down here. What about we start with this quantity? I know that you have seen this. Displacement. Now the question is it different from distance? So let's have distance down here. Well, it is. First of all, displacement is a vector quantity. So let's add this at the back. Displacement, a vector. Which means that you need both magnitude and direction for this. Distance, on the other hand, needs only the magnitude, and that is scalar quantity. Distance is a scalar. Now, in terms of meanings, they are quite different too. So let's take a look here. Displacement represents the shortest path between an object in space and a reference point. So let's make a note at the back here that displacement is for the shortest path. Between an object and a reference point. And usually we set the reference point to be the origin. We set this to origin. If you work with 3 dimensions, then it's 0, 0, 0. But if you work with 2 dimensions, then it's just 0, 0. Now the keywords are these: shortest path. Here we don't really care how this object travels in space. We only care about the final location it ends up at. And that's why sometimes we look at displacement as the position in space. So this is position in space. Now, distance, on the other hand, represents the actual path that the object travels in space before it reaches its last location. Distance is the actual path. That object travels in space. So the main difference is right here. Actual path versus shortest path. Now let's have a notation for displacement down here. Usually we use S for that. So S, and now we know that displacement has to be a vector. So I add vector sign right here at the top. And now I want this displacement to change over time. So I add this t. At different time, displacement can be different. At different time, the location in space can be different. So what you are looking at right here is a function of time. Function of time. In other words, f of t. Now that we have the displacement as a function of time, we want to study the rate of change of this displacement over time. So we want to study this rate of change of displacement s of t. And rate of change, by now we know that it's related to derivative. So all we need to do is to differentiate displacement. And we are going to get derivative of displacement with respect to time over here. D of s, once again a function of time with respect to t. And this is equal to velocity. And velocity has to be a vector too, both magnitude and the direction. And it also has to be a function of time. So let's make a box around this one right here. Displacement, and now we got the velocity, derivative of displacement. And now, what about we find the absolute value of this velocity? So let's do that over here. So we are going to find absolute value of velocity, and this one is speed. We only have the magnitude here. So make a note that this one is speed at time t. Now, we don't have to stop here. We can start to observe the rate of change of the velocity over time. So let's do that over here. We want to know the rate of change of velocity, vt. We know that we have to find the derivative of that. So let's diff velocity again. Let's diff this. We get derivative, and that is d of v t with respect to t. And this one is acceleration, which is a. And it has to be a vector. We need both magnitude and direction here. Also a function of time. So let's make a box around this. Okay, so we have three quantities here. First one, displacement. And second one, velocity, right here. And last one, acceleration. And this is the relationship between these three quantities we have seen in physics. You diff displacement, you get velocity. You diff velocity, you get the acceleration. Now, let's work on some examples in the next slide. In this example, we are going to shoot a rock straight up in the air, and then we have to answer a few questions here. First, let's take a look at what kind of information we have from the problem. Let's take a look here. So we know that a rock is going to get shot vertically up in the air, and it has the initial velocity of 49 meters per second. So this is the first piece of information we have here, 49 meters per second. And that is for the initial velocity. When you see this word, initial, you know right away that this is when t or time equal to 0. At the beginning of time or at the beginning of the experiment. And now we have velocity right here. We know that it's v. And not just that. We know that velocity has to be a vector quantity. It means that we need to care both the magnitude and the direction of this. So let's have the vector sign at the top. Now let's add something to this velocity. Let's make it depend on time. Let's make this v as a function of time. Now this velocity can be different at different time. Now let's take a look at the next information that we have here, and it's for the displacement. So we have the function for the displacement right here. That's good. So let's take a look at this. Function for displacement s of t equal to 49t minus 4.9t squared. And we know that displacement is also a vector quantity. It means that we have to consider both magnitude and direction. So let's add vector sign to this displacement s. At the top of this s, okay, let's make it black. Now that we have all the informations from the problem, let's put everything in a diagram. Let's do that on the left hand side. First, let's have ground. And now we have a rock on the ground. And this rock is going to get shot straight up like that. Okay, straight up. And now it has the initial velocity of 49 meters per second. So let's include that in the diagram. Okay, let me fix this. Let me put this rock on the ground. Something like that. Okay, this is better. Initial velocity 49 meters per second. So initial velocity v vector at the beginning of time, t equal to 0. V at 0 equal to, we know it's 49 meters per second. 49 meters per second. Now we know that velocity is vector quantity. It has to have both magnitude and direction. Now we have the magnitude, which is 49. Where is the direction? So we have to specify that. We know that this rock is going to get shot straight up, which means that this is the direction of this velocity, going up. Up. And it can be represented by this plus sign at the front of this 49. So we actually have this plus sign right here. So from now on, we know that the direction of going up is plus, and direction of going down is minus. Now we have all the informations. Let's take a look at the question that we have, the first one. We want to know, how high does the rock go? So what's going to happen here? This rock gets shot up, it's going to go up, and it's going to get slower. At some point it's going to stop, and it's going to come back down to the original location, something like that. So they want to know how high does the rock go. So basically they want to know the maximum height. Maximum height of this flight. So they want to know the height at this point. H max equal to what? At this point we don't know. So let's find out about that down here. A. But before that, let's add down right here for minus sign. So down direction has to be negative. Now back to A. Let's start with the displacement function, s of t. Let's bring that down here. S of t equal to 49t minus 4.9 t squared. So this is our main function right now. Displacement as a function of time, t. Now the question is, can we use this s of t to find h max, the value that we want to know? Can we use this to find the maximum height of the rock? Well, listen to this. Maximum height is the maximum distance from the ground to the top of the flight of the rock. Displacement, on the other hand, or you can call it s of t, can tell us about the position of the rock in the air. So they are quite similar. The distance from the ground and the position in the air, which means that we should be able to use s of t to find h max. However, there is one problem. Let's take a look here. In order for us to use s of t to find h max, we need to know the time. We need to know this input, time, in order to find displacement. However, at this point, we don't know how long it takes for the rock to get to the top. In other words, at this point, we don't know the time. Let's call the time right here T max. T max is still unknown at this point. So we have to find out about this. If we know this, then we can find h max according to this. Displacement at the top of the flight, T max. But this is unknown. We don't know. However, there is one thing we know. If we shoot a rock straight up, it has to stop somewhere before it comes down, which means that at the top of the flight, the velocity has to be 0. So at this point, velocity has to be 0. This is what we know. So let's use that. Velocity at the top of the flight, and the time of that is T max, equal to 0. It stops right here at the top. So we are going to use this equation right here and solve it to get T max. In order for us to use this equation, we need the velocity function, and we don't have that right now. So we don't have v of t at this point. So we have to derive that, and it can come from this displacement. At this point, we know that if we differentiate displacement, we get velocity. So let's do that. Let's diff displacement. So start with this s of t. We are going to diff this with respect to time. The result of this is the velocity equal to, let's use black, velocity depending on time too, equal to. Now we have to diff s of t, so let's diff this. 49t, you know that we are going to get 49 out of that. So here we have 49. Now we diff this, 4.9t squared. This is power rule. So 2 comes down, becomes minus 9.8. 9.8, and the power decreases by 1. So we have power of 1 right here, which I can take it out. So there you go. We have the function for the velocity. This one. V of t equal to 49 minus 9.8t. And we are going to come back to this equation right here. V of t max has to be equal to 0. So let's put t max in. So V of t max, 49 minus 9.8 t max, has to be equal to 0. Okay, so we are going to move things around. So we have this 9.8 t max equal to 49, which means that t max is equal to 49 divided by 9.8, and this is equal to 5 seconds. So now we know that t max equal to 5 seconds. So here, no longer unknown, and it's equal to 5. So let's put 5 right here, which means that we can find the h max by putting this 5 in right here. This is equal to 5. So let's work on this. So h max is going to be equal to 49 times 5 right here. So let me erase this dot. Okay, minus 4.95 squared. So what about I continue down here? We have more space. So h max, let's continue over here. Right now it's going to be equal to the first term, 49 times 5, we have 245. Alright, minus 4.9 times 25, and that is equal to 122.5. 122.5, and we have this equal to 122.5 meters for h max. And this is the answer for question A. This one right here, 122.5 is the maximum height. So let's put that right here. H max equal to 122.5 meters above the ground, and T max equal to 5 seconds. And that is the answer for question A. Now we move on to question B. First, let me split the screen right in the middle. And now we work on B. So what is it asking for? They want to know the velocity. This is what they want to know, v. At 78.4 meters above the ground. So this is our clue, 78.4 meters. So let's put this clue on the diagram. The maximum height is 122.5 meters, and we need to put 78.4 meters in. So it should be a little bit higher than the halfway of this flight. So somewhere around here. So let's assume that this point is 78.4 meters above the ground. 78.4 meter. And we want to know the velocity at this point. So at this point, right here, we want to know Vt equal to what? At this point, we don't know. So they want to know velocity, and we already have the velocity function from part A. Let's use that. So let's bring that over here. Vt equal to 49 minus 9.8 t. So this is our main function right now. And we want to use this to find the velocity at 78.4 meters above the ground. The question is, can we use this function right away? And the answer is no. Let's take a look here. In order to use this velocity function, we need to know the time. We need to know this input in order to find velocity. So we need to know the time that the rock takes in order to get to this 78.4 meters above the ground. We need to know the time right here. At this point, let's call it TB. At this point, let's assume that the time is TB. And we don't know what that is. And that's why we don't know the velocity at this time. TB equal to what? So this is going to be our main goal. We need to find out about this so that we can find velocity at TB. Let's put it right here. We want to find this v velocity at TB. And now we need to find TB. To do that, let's use the clue that we have, that is 78.4 meters above the ground, and that is displacement. So let's use the displacement function, s at TB. Okay, so at this time, it's going to be 49 TB. By the way, displacement function came from right here. You can use this, or this one is good too. 49 TB minus 4.9 TB square. And at TB, the height is 78.4. So this is our main equation, and we need to solve this for TB. So let's solve this one. Okay, first of all, let's put everything down here. Okay, 4.9 TB square minus 49 TB plus 78.4 equal to 0. And we want to solve this. First of all, I want to divide both sides with 4.9. So divide both sides 4.9. Divide this 4.9. What do I get here? I get TB square minus 10 TB plus this one, 78.4 divided by 4.9. I get 16 equal to 0. Okay, this looks good, which means that I can factorize this. It becomes t minus 2 and t minus 8 equal to 0. Solving this, I get t equal to 2 and 8. So at this point, I know that t equal to 2 and 8. Now, why do we have two values of time here? 2 seconds and 8 seconds. We are supposed to find the TB right here, but it turns out that we have two values. And the answer is because the rock passes this height twice. Let's take a look here. The rock starts right here and it takes 2 seconds to get to this 78.4 meters. 2 seconds to get to here. And it takes 3 more seconds to get to the top. And that's why it gets to the top at 5 seconds. And then it has to come down. And it's going to come down to this height again. And at this point, it's going to be 8 seconds. So as you can see here, it passes this height twice. One right here, first one, and the second time right here. So that's why we have 2 values of time. The first time it passes when it goes up, and the second time it passes when it comes down. So we have to consider both. Now we are going to put these 2 values in to the velocity function. So let's do that down here. First, v at 2 seconds on its way up. At 2 seconds, we have 49 minus 9.8 times 2. And we have 29.4 meters per second. And velocity at 8 seconds equal to 49 minus 9.8 times 8. And for this one, we have minus 29.4 meters per second. So let's take a look here. We have different signs. This one is positive and this one is negative. What is it telling us? Positive means that it's going up. So when you see this, you know that it's going up because up direction is positive here. And minus sign right here, we know that it's coming down. And there you go. That is the answer for question B. We have 2 velocities here. One at 2 seconds and the other one at 8 seconds. And now we move on to question C. Let's do that on the next slide. So question C, what is it asking for? Let's take a look here. What is the acceleration? They want to know acceleration at all time. So they want to know A. At this point, we know that the rate of change of velocity is the acceleration. So let's make a note right here. Part C, rate of change of v is acceleration. So all we need to do in order to find acceleration is to differentiate velocity function. So let's start with the velocity function here. So velocity function we have from part B and part A equal to 49 minus 9.8 t. So we need to diff this. Vt, diff this with respect to time. And it's going to be equal to, now we diff this, constant, it goes to 0. And we diff this, minus 9.8t, we are going to get this, minus 9.8. And there you go, this is the acceleration. And as you can see here, we have this minus sign right here. What is it telling us? It means that it accelerates down. So from this, we know this is acceleration down. Of course, this is gravitational acceleration. It has to point down. And that is the answer for question C. This one is easy. So the answer is, what about we put it right here? Acceleration at all time equal to a constant value, minus 9.8 meter per second square. Okay, answer for part C. Now let's move on to question D. What is it asking for? They want to know how long the rock stays airborne. How long it stays airborne. In other words, they want to know the total time. So let's make a note down here. Total time that the rock takes to go up, get to the top, and come back down. So let's work on this down here, part D. But before that, let's have a diagram up here. So we have ground, and then we have a rock, and now we shoot it up, so it goes up. And it gets to the top and comes back down to be on the ground again. So this will happen. And there is one thing we know for sure is that the displacement on the ground has to be equal to 0. Right here at the reference, displacement S must be equal to 0 on ground. And this is our main clue. We are going to use this to solve for total time. And as you can see here, the information that we have is displacement. So we are going to make use of this displacement function up here for part D. So let's start with that. S of t equal to 49t minus 4.9 t squared. And now let's assume Tg to be the time that the rock is on the ground. So let's set Tg right here to be the time that rock is on ground. Now we solve for Tg, and let's do that over here. Displacement S at Tg, the time on the ground, equal to 49 Tg minus 4.9 Tg squared. Now let's take a look here. This is the displacement when the rock is on the ground, which means that it has to be equal to 0. So this is equal to 0. And when you see this, you know it's on the ground. Now we have this quadratic equation to solve, this one right here. One equation, one variable, Tg. Now let's start by divide both sides with 4.9. 4.9 and 4.9 here. And now I get 10 Tg minus Tg squared equal to 0. And now I multiply both sides with minus 1. Multiply with minus 1 both sides, I get Tg squared minus 10 Tg equal to 0. And now I take the common term to the front. Tg at the front, and then I have this Tg minus 10 at the back equal to 0. Now I solve this and I get two values of Tg. Tg equal to 0 and 10. Now the question is, why do we have two values of Tg's? And the reason for that is because the rock is on the ground twice in this motion. Let's take a look here. At the beginning of time, when the rock is on the ground, at t equal to 0, the displacement is equal to 0. And then we shoot it up, and it goes up, get to the top, and comes back down to be on the ground again. And it comes back down at t equal to 10. And that's why the total time for this flight, right here, let's answer. Total time equal to 10 seconds for the rock to go up, get to the top, and come back down. And that is the answer for question D. Now, there is an easier way to answer this, and we are going to use the information from part A. From part A, we learned that it takes 5 seconds for this rock to get to the top. It takes 5 seconds to get to here. It means that it has to take another 5 seconds to come back down, right? Come back down with another 5 seconds. So if we add these two together, it becomes 10 seconds for the total time. And that is another way to find the answer for part D. In this example, we have a water tank and it's draining. That's what we know, draining water tank. The starting time, once again at t equal to 0. However, the unit is minute. Keep this in mind. This is different from what we had in example number 1. In that one we had seconds, but here it's minute. Now we also know the volume of the water, and it's given by this function right here, Q of t. So this is our main function. Q of t can tell us the amount of the water in the tank at different times. And the unit is in liters. Check it out here. Keep this in mind too. So this is our main function. We need to work on this. If we know the time, we know the amount of water at that time. Now, before we try to answer these questions, let's have some diagram on the left-hand side. Ground right here. And then a water tank. Something like this. Stands. And just in case you don't know what this is, I'm gonna say this is water tank. So you can't deny on this. And now we have the pipe at the bottom. And it's draining water out. So we have this scenario set up, and now we try to answer a few questions here. But first of all, let's take a look at C right here. We need to change something. So it says that we need to find the average draining speed in the first 10 minutes. So let's change this in the first 10 minutes. Cross it out and change it to during the whole session. Whole session. In other words, until the tank is empty. Okay, tank is empty. Now let's take a look at some basic information we can get out of this main function that we have, Q of t. What about we want to know the amount of water at the start of time at t equal to 0 minute. So let's check this out. Amount of water at the start, t equal to 0. Q of 0 equal to. Now we can use this function right away. So let's put 0 in. So we have 200 times 30 minus 0 square. So we have 200 times 900, and that is equal to 180,000, and the unit is liters. So let's put it right here, liters. So at the start, we have 180,000 liters in the tank. Now, if I ask you this question, how long does it take for the tank to be empty? Now, let's find out about that. So let's take a look at this QT right here. We want this to be 0, empty tank. What if we set this t right here to be 30, so that the inside of this parenthesis becomes 0? So let's try that. Let's check amount of water at half an hour, 30 minutes. It's going to be equal to 200 times 30 minus 30 square. So these two are going to go to 0. So we have 200 times 0, and that is equal to 0 liters. In other words, an empty tank, no water left. Empty. So the whole session is going to take 30 minutes, starting from 180,000 liters until nothing left. Now let's work on part A. Part A, let's see what they ask for. They want to know how fast is the water draining at the start. So let's check some keywords here. How fast the water is draining. So basically, they want to know the rate of change of the amount of water at the start. So talking about this rate of change, that is how fast. Of the amount of water, and that is Q of t. We have the function here, so let's use it, Q of t. So we need to know the rate of change of Q of t, and by now we know that that is related to derivative of Q with respect to t. So we need to differentiate Q. So let's do that down here. Let's start with the QT. So QT equal to 200 times 30 minus t square. And we have to differentiate this to get the rate of change. So let's do that. Let's diff q of t. Q of t, and now we diff with respect to time. So let's take a look here. This function, q of t. We need to diff this. But looking at this, I think I see a function inside a function here. So what about we group these two together inside a box? 30 minus t inside this box. And this box has square outside. So this is definitely a composite of several functions. So we need chain rule for this one. So for this one, we need to use chain rule to diff this. So we are going to diff one after another, starting from the most outside function, and then we proceed to the next one. So looking at this, I think the most outside function is the square. So I'm going to work on this one, square right here. So diff the square, I use the power rule. So power is going to come down. So this is equal to 200 is still there, not changing. So 2 comes down to the front, and now I keep the box the same. I keep the inside function unchanged. So this box right here, not changing that. So inside we still have this 30 minus t, and now the power decreases by 1, so we have power of 1 right here. Now we are done with the outside function. Let's move on to the inside function, which is 30 minus t. We need to diff this with respect to time. We diff 30 with respect to time, that is constant, is going to go to 0. We diff minus t, we get minus 1. So minus 1 is the second term from the second layer, the inside function. And now we multiply them together, and that is the complete chain rule for this function. Okay, let's combine these terms. So what do we have here? Equal to minus 400 times 30 minus t. And this is q prime as a function of t. So let's make a note right here that this is q prime, derivative of q with respect to t as a function of time. Now let's take a look at question A. They want to know how fast the water is draining at the start. We have the q prime right here, so we are ready to use this. At the start, that is when t equal to 0. So let's work on this. So we know for A, t has to be equal to 0. So let's find q prime at 0. Equal to what? Equal to minus 400 times 30 minus 0. 0 minute. So what do we have here? It's equal to minus 12,000. And the unit is liters per minute. So let's take a look at this minus sign right here. This one, what is it telling us? Minus sign. It tells us that the water is decreasing. So let's make a note right here. Water is decreasing with this minus sign. If you have a plus sign, then it's increasing. Now let's move on to part B. Let's work on that on the right hand side. Okay, part B. What do they want to know? Let's take a look here. They want to know how fast the water is draining. Once again, rate of change of Q. We have Q prime here, so this should be easy. When the time is at 10 minutes. Okay, so this is what they want to know. T equal to 10. And they want to know Q prime, so let's put everything in. Q prime at T equal to 10 minutes. 10 equal to minus 400 times, same thing, 30 minus 10 this time. So we have minus 8,000 for this part B, and the unit is liters per minute again. Once again, we have this minus sign, so we know it's the water is decreasing. So make a note, decreasing. And as you can see here, compared to A, the water is decreasing slower. This one is minus 8,000 and part A is 12,000. So this one is slower. Slower than A. Okay, that is part B. Now let's move on to part C. Down here. So what do they want to know? They want us to find the average draining speed. So let's take a look at this word. Average. This is the key. Draining speed. So this one is different. Before it was how fast, but now it's average. So let's take a look here. Average. When you see this word, it refers to the whole session, the whole interval. So let's make a note. Average means whole session. Or whole interval. The total time. So let's find it right here. Average draining speed. For this, it's not going to be equal to, this one not equal to dq by dt, because dq by dt is the speed at a particular point, but average is the whole session. So we have to use a different formula, and that is equal to delta Q divided by delta T, the whole amount of water and the whole time, the total time. So what is this equal to? Equal to Q at the end of the session, 30 minutes, that's when the tank is empty, minus Q at the beginning, Q0, divided by the total time, and that is 30 minutes. So this is going to be equal to, at the end, right here, Q30, we know it already, it's equal to 0 right here. So let's put 0 in. So we have 0 minus Q at the beginning. We also know it right here. Right here. So we have 800,000 right here divided by 30. And this is equal to minus 6,000 liters per minute. And that is the average draining speed for part C.